Problem number 8, the pinball machine. So again, a pinball is a solid sphere. And if it didn't say that, I apologize. There we go. So there's our rotational inertia. All right, it tells us the mass of the ball is 0.25 kilograms. The spring has a spring constant. What's the symbol for spring constant, you guys? K. Lowercase letter K, right? So our spring constant is 150 newtons per meter. All right, and it's pulled back a distance of 8 centimeters, held at rest, and then released. Question A wants to know the velocity of the ball as it leaves the plunger, and B wants to know how far it goes up before it stops and rolls back down. We're oversimplifying and assuming it doesn't hit anything, okay? So here's your drawing. So at this point, here's the thing being held at rest, okay? What type of energy is it going to have at this point, you guys? So we've just pulled the thing back. We haven't released the plunger yet. So we've just got elastic potential energy, right? Then you let it go, and it goes ka-chunk up to here. That's the point where it leaves. So at that point, what type of energy does it have now? It's got kinetic energy, gravitational potential energy, and rotational kinetic energy. I am unhappy with how I wrote that. Okay? Does that make sense, you guys? All right. Question A wants to know what's the velocity at that point. Follow? All right. And then question C says, all right, question B says the ball is going to go up, slow down, stop, and come back down. So when it gets to this point, how far has it rolled? So question B wants to know how far it rolled to get to that point, right? What types of energy does it have at that point, you guys? GPE. What important thing happens at that point, you guys? It stops, right? So all of the energy there is GPE, right? Follow? All right, so I haven't done any calculations yet. I've just kind of thought conceptually about what's going on. Does everybody understand my crappy notation and weird little drawing here? Okay, now, there's one other, I guess, important piece of information that we know, which I've not yet identified, which is this. The problem tells us the machine is inclined at, is it 20 degrees? And it tells you that you compress the spring 8 centimeters. What can I use that 8 centimeters to find? The height at which color point? At the red point, right? Does that make sense? Like the ball is here, and then I pull the plunger back, 8 centimeters, and then I'm going to let it go. So it's going to go ka-chunk, right? And release it at this instant. And at that instant, the height is going to be, whatever this little height is, right? So I'm looking at a triangle that looks like this, 8 centimeters, 20 degrees. Find this. This height turns out to be 2.74? 2.7 centimeters, or 0.027 meters, right? And I wish I'd written that all in red because it corresponds to that red point. So I'm sorry I didn't do that. No, because your elastic potential energy is going to be in joules, which has meters intrinsically built into it. Does that make sense? Because a joule is a Newton meter, not a Newton centimeter. Yeah, so I converted it there at the end. All right, are we good or no? Any problems? All right, so total energy should be constant, right? Do I need to explain why the total energy is constant, you guys? Yes? So what forces act on it? So shout out some forces that act on it during the course of the motion. Gravity. Why don't we need to worry about gravity? It's a conservative force, so that's not going to change our total energy. What other forces are there? Somebody said friction. Why don't we need to worry about friction? Yeah, it's that fixed point thing, right? Your displacement at the point of contact is 0, right? So it's just like constantly tipping over, right? So friction doesn't do work. so it doesn't change the total energy. So we got gravity, we got friction, force of the spring. Why don't we need to worry about the force from the spring? It's a conservative force, right? That's why we have EPE, because the elastic force is a conservative force. All right, so we got gravity, elastic, friction, and normal force, which is perpendicular. Cool? Friction is the one that's new. Are we okay with that idea that the ball is just constantly tipping over? Is that a question, Alex, or you just...
Yes, question.
Yeah.
So you say that EPE is conservative, but like you only mean from like, let's say you pull it back, you only mean from like once you let it go. Like when you pull it back, how does your hands?
Yeah, so that's the force of heat, right? Good? Yeah, and the problem starts when you let go of it, right? To be clear, it's not the EPE that's conservative, it's the elastic force that's conservative, not the energy. That's a nitpicky thing, but... All right, are we good? All right, let's name these points. Let's call this one S for start, and then we'll call this A and B. Follow? All right, so here we go. The total energy at the start should equal the total energy at point A, yes? So let's see, at the start, what type of energy did we say we had? EPE. So the EPE at the start should equal the total energy at A, which is GPE at A plus the KE at A plus the RKE at A. Everybody good? All right, so EPE, let's see, that's 1/2 times K times X. What's my X, you guys? I haven't explicitly written it down. It's how far you pulled it back, which was 8 centimeters. So should I put in 8? 0.08, right? Don't forget to square it. So 1/2 K X squared. Everybody good with that? All right, equals, let's see, GPE at A. Let's see, that's the mass of the ball, which was given to you to be 0.25, right? Times G, which is 9.8, times the height, which is this thing. So that's my GPE. Everybody good? Plus the kinetic energy at that point. Well, let's see, that's 1/2. What's the mass? Just the mass of the ball, 0.25. Why doesn't the mass cancel out in this problem, you guys? Because EPE doesn't have mass in it, right? Good. Are you guys going to fight? Do I need to? I can separate you two. All right, don't make me turn this classroom around. Okay. All right, times V squared, right? So that's my KE. Good. Plus RKE. How am I going to deal with the RKE? 2/5 times the KE, right? 2/5 times the KE. Cool? Who's got questions? I can't stop playing with this. Can you? All right. Okay. So let's see. So this mess here gives you a number. Is it 0.04? Nope, 0.48. Is that right?
Yeah.
Joules equals this mess. So somewhere I have a calculatrix. So let's see, clear 0.25 times 9.8 times 0.027. So the GPE is 0.066. The KE is 0.125 V squared. And the RKE is 0.05 or 005? 0.05 V squared. Let me clear this up. This is kind of crappy writing. 0.125 V squared. Good, you guys? And do you guys understand these are like terms, so I can just add them up? So I get 0.48 equals 0.066 plus 0.175 v squared, and then solve for v. Problems, you guys? Okay, so solve for v and it gives you whatever I said the answer was on the sheet. What does it turn out to, you guys? Sorry? 1.52. All right, so does that make sense, you guys? All right, cool. Now, the next question says, how far up the ramp does it roll before it stops and comes back down? So now, instead of comparing the start with point A, I want to compare some point with point B. Does it matter which point I pick? No. Which is the easy choice? The start, because I already know my EPE is 0.48. All right, so let's see. If I compare, so now what I'm doing is this. The total energy at the start has got to equal the total energy at point B. Well, we already know the total energy at the start. It's 0.48 joules. That's got to equal, what type of energy do we have at point B, you guys? Just GPE, right? Oh, so that's 0.25 times 9.8 times H. Are we good or no? All right, so divide both sides and you find out that your height is a number that nobody's going to tell me. I'm sorry for being so horribly unprepared. 0.48 divided by 2.45. So you get 0.196 meters. What's wrong?
Where did the 12 come from?
The 12? Oh, that's, I don't know where that came from. It's garbage left over from last hour. No, you're okay. Sorry. Gotcha. My bad. Yeah, so here's our velocity. I apparently added in an extra slide by accident. Oh my gosh, what is going on? What am I doing? There we go. Ha! There we go. All right. Everybody good? All right. So there's my height. Am I done? No, I need to figure out how far it rolled. But look, that's the worst right triangle ever drawn by a human being. Deal with it. 20 degrees, 0.196 meters. I want to know how far it rolled. So do a little bit of trigonometry. You divide by the sine of 20 degrees, and that'll give you your displacement. Cool? Everybody happy? Anybody unhappy? Okay. That was number 8.